Hello everyone, I'm Soramichi Akiyama from the University of Tokyo, Japan. The random access latency of DRAM has not improved much for decades, or it is even worsening. For example, TLCD, a latency parameter, was 12.5 nanosecond in DDR3 1600, but it is still 13.75 nanosecond in DDR5 3200. On the other hand, the CPU core speed had been exponentially increasing until recent years, as we can see in the figure on the right. Note that the y-axis is log-scaled. For example, we experienced almost 100x speedup between year 2000 and year 2015. Therefore, the impact of DRAM latency to overall application performance is ever enlarging. Approximate memory is a new technology to reduce DRAM access latency. It operates DRAM roughly but quickly to achieve shorter latency, but it incurs higher error rate or higher bit flip rate. It does this by violating the timing constraints of internal electric operations of DRAM. So here's an example. Memory cells, each of which contains 1 bit of data, are organized as rows and columns. And before a read request can be issued, an entire row of the cells has to be copied to the buffer. And the buffer becomes electrically stable after 12.5 nanosecond in DDR3 1600. However, an existing work found that the values can be read with some errors even before that, for example, just after 7.5 nanosecond. We refer the minimum size of a continuous memory region that has the same error rate to as approximation granularity. Because all the time is controlled per row, as we saw in the previous slide, approximation granularity is equal to the size of DRAM row, which is from 5 terabytes to a few kilobytes in real DRAM chips. For example, in the left side of the figure, an entire 5 terabytes is controlled by the same timing. Therefore, all the data inside that region has the same error rate in average. So here comes the granularity gap problem. It is a mismatch between approximation granularity and granularity of data criticality. For example, this data structure represents a graph node that has ID and pointers to other nodes and the score of the node. And ID and the pointers are critical data because no error is allowed to be injected into this data, while the score of the node is non-critical data because small errors do not affect the result that much. The problem is that this data structure cannot be mapped to approximate memory because the approximation granularity, 5 terabytes, is way larger than the criticality of the fields. In this case, we want to protect our ID and pointers because they are critical data, while we want to allow faster access to the score field. A possible solution to the problem is memory layout conversion. In general, array of structures AOS can be converted into structure of arrays SOA at compile time. For example, the data structure shown in the left side of the figure can be converted as shown in the right side of the figure, where each field of the original struct, X and Y, now consists a distinct array. The good point of this conversion is that one field consists a large memory region, so it can alleviate the granularity gap problem. However, the bad point is that one struct instance is split into a large memory region, so it may cause possible performance loss due to the decreased access locality. Our claim in this paper is that the granularity gap problem is a significant concern in using approximate memory. Why is that? Because the memory layout conversion might incur as large overhead as the benefit of approximate memory, in which case there is no off-the-shelf method to easily solve the granularity gap problem. To support this claim, we conduct quantitative overhead analysis of memory layout conversion, and we are the first to discuss quantitative slowdown caused by the granularity gap problem. We analyzed slowdown of spec CPU 2017 benchmarks caused by memory layout conversion. The idea is to use Gen 5, a CPU and memory simulator, to mimic memory layout conversion. This frees us from using complex compile time techniques that have no off-the-shelf implementation. The analysis procedure is as follows. First, we detect the most cache-unfriendly data structure in each benchmark. Second, we apply memory layout conversion to the detected data structure because approximate memory is the most useful when applied to data that incurs a lot of cache misses. And third, we compare performance in every possible memory layout conversion pattern. Please refer to the extended version of our paper on arXiv for the first part. Here's how to mimic memory layout conversion with Gem5. The point is to remap physical addresses of structure fields to split one structure into two at runtime. This is completely done inside the simulated CPU, so no modification is required to the benchmark code. For example, in the figure, the structure is converted so that each member, X and Y, consists a distinct array. To do this, we implement a module called address remapper into Gem5. The address remapper takes an original address of a memory access instruction and returns a remapped address. For example, on the right, the address 408 is converted into address F00 because address 408 points to member Y, which has to be split away from member X. For the experiment, we analyzed three benchmarks from Spec CPU 2017, MCF-R, DPSN-R, and NAMD-R. The most cache-unfriendly data structure of them are array of structures as shown in the table on the bottom left. In the table, the bracket means that the data structure is an array, S means that it is a structure, P means it contains a pointer, F means it contains a floating point number, and I means that it contains an integer. For the simulation, we skip the initial phase of each application and only phase 3 simulate the main loop. We measure the number of simulated micro operations within a fixed length of time in the simulated world. The configuration of the simulated processor and memory are shown on the bottom right. The graph shows the results for MCF-R. There are 256 memory layout conversion patterns, and each bar shows the number of simulated micro operations for each configuration normalized to the non-conversion case. The rightmost bar, colored red, shows the average. In the worst case, it experienced 8.13% slowdown, while in the best case, it experienced 0.77% speedup. In average, it experienced 3.81% slowdown. Note that we only consider the effect of memory layout conversion, and we do not do not simulate the speedup caused by approximate memory. DPSN-R experienced 2.91% slowdown in the worst case, 0.02% speed up in the best case, and 1.16% slowdown in average. NAMD-R did not experience much performance difference. Please refer our paper and the extended version of it for more detailed experimental results. Here we compare the experimental result with the benefit of approximate memory. Again, the overhead caused by memory layout conversion for MCF-R is 3.81% in average and 8.13% in the worst case. On the other hand, the speedup caused by approximate memory is estimated to 4 to 5%, averaged across all Spec CPU 2006 benchmarks when bit flips are not allowed. So let's assume twice as much speedup, 8 to 10%, if we allow bit flips to be injected to the data. Another research estimated that the energy reduction given by approximate memories is about 12.5% for the overall energy, meaning that CPU and memory are all considered when bit flips are allowed. Comparing these numbers, we claim that the granularity gap problem incurs non-negligible overhead, and it is a serious concern in using approximate memory. Here's conclusion on the future work. The conclusion is, again, the granularity gap problem is a significant concern in using approximate memory because the benefit of approximate memory could be cancelled out in some cases. And we believe that the problem needs more attention and effort from the research community. The future work obviously is solving the problem. And the basic idea we have is to fetch two or more fields in separate memory locations at once when they are predicted to be used closely in time. However, we've been facing some challenges and we have not yet achieved it yet. Any questions and comments are welcome in any communication channel, for example, to this email address. Thank you very much for listening.